Hello everyone, this is Martha from the Academic Support Center once again, and this is a calculus video about related rates. Let's jump in and see what we can get done. We're going to start off with a few reminders. The first is that derivatives are rates of change. We've learned all these rules about how to take a derivative and what they mean, but at the base there, we can look at them as rates of change, right? Now, sometimes things change in the increasing direction, and sometimes it's in the decreasing direction. Our slope can go up or down. So if something is growing in size, the derivative is going to be positive. Now if something's shrinking or deflating, the derivative, that rate, is negative. So those are our first two reminders. Our last reminder has to do with how we take derivatives. Now we can have a variable y to the sixth, right? And if we take the derivative with respect to x, we end up with dy over dx, right? And that's when we bring in the power rule. So it's 6y to the fifth. And with related rate problems, we're going to be taking a lot of derivatives with respect to time. And so that means that sometimes we'll have equations with more than one variable. Things are growing in more than one direction. And we need to remember that we're going to take each derivative with respect to time. So let's say that we have x squared plus 4y to the third. And we take the derivative with respect to time of each of them. So the first one, we bring that power rule, it's going to be 2x, and it's going to be dx over dt. That's how the x is changing with respect to time. Then we would do plus, we bring that 3 down, 4 times 3 is 12. It would be 12y squared. And then we would have dy over dt. And these derivatives are the rates at which x or y, respectively, are changing. And it's important to remember that these are rates in the problems, and we need to identify which rate goes with which variable. Oftentimes, related rate problems are word problems, and there are a few things that can help us make these problems a little bit easier. The first is to read the problem carefully and identify given information. If something is a rate, remember that it's the derivative with respect to time. Check your units. This is pretty important. Sometimes they'll switch between minutes, seconds, meters, kilometers. Just check your units and make sure that they're consistent. And I'm going to show you a technique using a reference box where I put it on the side. You can put it on the top, you can put it on the other side, but that's just kind of to help condense your information and keep it together. So those are the first things. The next thing that you want to do is to draw a diagram. This can be extremely helpful when picturing a problem. The next tip is to find equations that express relationships between variables. They can be equations for volume, area, surface area, any of those. So be on the lookout for what relationships we know and how we can express those relationships. So once that's all set up, we take the derivative of different equations. We're going to substitute rates that we're given as derivatives for known variables and solve for the missing variable. Now after all that is said and done, we still want to double check units to make sure that we're staying consistent. So those are helpful tips to read carefully, identify information, draw a diagram, find those equations, and figure out what we need to derive for. All right, so we're going to jump in with a couple of examples from the book. And it's from the third edition of Calculus Early Transcendentals. This example comes from page 227. So example 1 reads, spreading oil. An oil rig springs a leak in calm seas. And the oil spreads in a circular patch around the ring. So we know that we're going to be dealing with circles. So draw a little circle, circular patch. Now, if the radius of the oil patch increases at a rate of 30 meters per hour, so I know that my radius with respect to time is 30 meters per hour. That's my derivative. That's how the radius is changing. Now I need to know, the question then asks, how fast is the area of the patch increasing? So I need to find what I'm looking for is the derivative of the area with respect to time, because that's the rate there. Now, so how fast is that area of the patch increasing when the patch has a radius of 100 meters? So let's make a box over here to put everything that we know. We know that it's a circle. We know that the derivative of the rate of the radius is changing at 30 meters per hour. We know that we're looking for the derivative of the area with respect to time. And we want when the radius, or when r, equals 100. And we're given a nice graphic up here, so we don't have to draw a diagram for this. We've got the oil rig and then how everything is spreading. So what equation can we use to pull all this together? Well, we've already been told that we want the area. So the area of a circle, that equation is pi r squared. And it's actually the area in relation to time, pi r radius in relation to time squared. So we're going to take, our next step is then to derive each of these. So we want the derivative of the area with respect to time equals, now pi is just a constant. So that r squared, we take the derivative of that, so that's 2r. And then we also have to remember that we're multiplying by the rate that the radius is expanding, that dr dt. Now at this point, we've got most of the information that we need. We can then plug in what we know. We know that we're looking for the derivative with respect to time, so that's good. 2 pi stays the same because those are constants. The radius at the given time is 100, so that goes there. And we're also given that rate that the radius is expanding, which is 30 meters per hour. I forgot actually that this is 100 meters. So let's keep that in there. And now it's just a simple process of plugging in all of our numbers and going from there. Now with this, we can multiply 2 times 100 to get 200 pi meters. And then we multiply 200 times 30 meters per hour. 2 times 3 is 6, and so we add all the zeros, we get 6,000 pi meters. Meters is meters squared per hour, and that's the derivative of how the area is changing in relation to time. And that's our answer. Quick review, oftentimes to check your units, volume, remember, is going to be units cubed. Area, you're going to have units squared. If it's just length, width, height, whatever, if it's one-dimensional, your units are in singular form. So because we're dealing with area, our units are squared. All right, our last problem for this slide. We're going to draw our box over here. We've got 2 planes approaching an airport, so we're going to have this be the airport. One flying due west at a rate of 120 miles per hour. So that's my rate over here. D over dt is 120 miles per hour. And then the other plane flying due north has a rate of 150 miles per hour. So that's my derivative on that side. And if I look, because they're flying at the same constant elevation, this relationship can be expressed as a right triangle, which helps us out. Now let's see what else we have from the problem. We're given that we want to know how fast is the distance between the planes changing. So we want to find the derivative of that distance with respect to time, and we're going to call that z for our hypotenuse. Now, how fast is that changing when the distance of the westbound plane is 180 miles and the northbound plane is 225 miles? So we know that we can express this as a right triangle with the formula z squared for our hypotenuse equals x squared plus y squared. And we can also find that we know that derivative of x with relation to time is 120 miles per hour, that the distance, or that x, is 180 miles, and we know that the distance, or the derivative of y with respect to time, is 150 miles per hour, and then we know that our y is 225. We need to find our z, so let's do that really quickly. We get z squared equals 180 squared plus 225 squared. That gives us that z equals 83, z squared equals 83,025. If we take the square root of both sides, we get that z is approximately 288.141. Now we put that into our reference box over here, and we have all of our information ready to go. So we're going to start by deriving. We take the derivative of this equation here. That gets us 2z, and the derivative of z with respect to time, which is what we want to solve for. And that equals the derivative of x squared is 2x dx dt, plus the derivative of y squared is 2y dy dt. Now I'm going to just divide everything by 2, make life a little bit simpler, and we're going to solve for dz dt. So we've got that z dz dt equals x dx plus y dy. And we can start putting in numbers here at this point, but let's try dividing by z. And really this is just manipulating the formula first. So we've got dz over dt equals x times dx plus y dy, and the dx and dy are both with respect to time, over z. So we can fill in what we know from our reference box. So we get that dz over dt, which is what we're looking for, equals x is 180 miles times the derivative of x with respect to time, which is 120 miles per hour, plus y, which that distance that we're given in the problem is 225, times that derivative, or that rate of 150 miles per hour, over z, which is about 288.141. Then it's just a problem of plugging the numbers into the calculator, and what we get out, real quick, something very important. These rates are negative because that space is decreasing. So we can't forget that those rates are negative because we're getting closer and closer. So after we do all of our computations with this, we're going to get the result that dz over dt, or the distance changing, is approximately negative 192 miles per hour. And it's negative because they're getting closer and closer together. Hope this helps. Have a great day.